All right, how's everyone doing? All right, so today we're going to go ahead and we're going to cover a new component. We've been using resistors and doing our network analysis techniques and all of that. Time to get into some new components. There's a lot more out there in electronics than just resistors. So we're going to actually start with a diode. Now, the schematic symbol for a diode is, as you can see right here, it looks like a triangle with one flat side, and we actually have a name for either one of these sides. Back here, this is the anode, and over here is the cathode. Okay, and here's the main feature about a diode. It only allows current to flow in one direction. So in other words, it will allow current to flow from left to right here in the direction of this current arrow, but it won't allow current to go back through the device. And that's actually kind of inherent in this schematic symbol. If you notice, it kind of looks like an arrow that only that is pointing in this direction. And that's just to signify sort of intuitively that it's only allowing current to flow in one direction. Okay, so again, it won't allow current to flow backwards, but it will allow current to flow forwards. Okay, and the back here is the anode, and the front half is the cathode. Okay, and that's our schematic symbol. Now, as far as a physical device, there are several different kinds of diodes. We have LEDs, rectifier diodes, and signal diodes. LEDs, of course, are those things that light up, and this name of LED, or you'll hear some people on the internet, they'll just call them LEDs. I tend to say LED. LED is actually an acronym for light emitting diode. Okay, so an LED is a diode. We also have rectifier diodes, and we also have signal diodes. These are kind of, I'm just going to label these as our three major classes of diodes that we're going to be seeing in 211 and in 311. And that's just sort of the physical device. Okay. Now, of course, the LED, being a diode, it only allows current to flow here from positive to negative, but it has this side effect, this byproduct of producing light when it does, when current is flowing through it. And in fact, I'm going to use an LED for our future examples. Okay, so like I said, the main characteristic of a diode is that it only allows current to flow in one direction. So let's go ahead and kind of see what that sort of means. Okay, so I'm going to go ahead and let's set up this diode here with a voltage source. Okay, so I've done that. We have a diode, and we know current is only going to flow in one direction. Now, if we look at the polarity of our voltage source, right now our voltage source is telling us we're trying to push current in this direction. Now, this diode, like I said, it's only going to allow current to flow in the same direction as it's pointing, right? From positive to minus. Well, it is. So we are going to have current flowing in this situation. I'll just say that I is greater than 0 amps. So we do have current flowing from the anode to the cathode. Now, when we have our diode such that current is flowing through it, we call that forward biased. Okay, biasing or biased is just a fancy way of saying which way your polarity is applied. So our polarity, we have positive applied to the anode, minus applied to the cathode. So we're creating a situation such that we are causing current to flow from the anode to the cathode. And because of the orientation of this diode, it's going to permit that. And in fact, we can treat this for right now like a closed switch, okay? Because the current is flowing, this diode is conducting, and so it's allowing the current to flow through. And in fact, when we treat a diode like just a simple switch as being open or closed in this case, we refer to that as the first approximation. Okay, we'll talk about the second approximation later. But for right now, let's go ahead and let's just imagine this diode is simply acting like a switch that is either closed or open depending on how the polarity is applied. By that I mean we're applying positive here and minus there. We're causing the current to go from left to right or in the direction of this arrow. And so this diode is forward biased, okay? Now let's go ahead and set up the opposite of that. So same kind of circuit, except I'm going to go ahead and I'm going to flip this voltage source upside down. Now the positive's on the bottom, minus is on the top. Orientation of the diode, I'm leaving the same. And now notice we've applied positive here, minus here. So we're trying to cause the current to flow in this direction. Now, what that means is this diode is going to now not be conducting. So in other words, this diode is going to behave like an open switch, not conducting. Now, if this is true, we call this reverse biased. Okay, so notice the only thing we changed was the direction of the current. So in this direction, this diode is not going to permit current to flow. So in this case, I is now going to be equal to 0 amps. Okay, so here's our forward biased versus reverse biased. To a first approximation, we're just treating it like a closed switch or an open switch, depending on which way we're causing the current to flow through the device. Okay, so forward bias just means we're trying to, or we are pushing current through the device in that direction that it'll allow current to flow. Or reverse biased, we're pushing current in the opposite direction, at which point our diode is not conducting, or to a first approximation, it's acting like an open switch. Okay, so this is sort of the basic principle of how a diode is supposed to work, or how a diode does work. Now, in order to get into the second approximation is just a slightly deeper understanding of how a diode operates, and it's a little more accurate for real world. Now, for that, I'm going to go ahead and use, for example, an LED. Now, for an LED, An LED being a light emitting diode. The schematic symbol stays the same, except we're just going to add this squiggly arrow coming off on the side to indicate that light is emitting from this diode. But for all practical purposes, this LED is just a diode. Again, it'll only allow current to flow in that direction. It won't allow current to flow in this direction. Okay, so we need to make sure that we forward bias it and we apply our positive up here, our minus down there, and we actually cause the current to go downward through this diode. Now, the reason I like to use LEDs as sort of a demonstration for understanding diodes is because when they are conducting, they give off light. And when they're not conducting, they don't give off light. Okay, I think for computer science majors, they love writing hello world programs. You know, that first bit of code you type into the computer and it spits back and it goes, hello world. For computer engineers, I think we just like blinking lights. I like to use the example of an LED just because it's got that visual indication of whether it's conducting or not. So let's go ahead and let's set that up and see what that looks like. Okay, so again, I'm going to compare the forward bias to reverse bias. So in one case, I'm going to apply my polarity correctly. And in this case, we have applied the positive to the anode and the minus to the cathode. And so in this case, we are forward biased. And so, yes, we do get light coming off of this. However, again, if I flip the polarity on this, and now I'm going to go ahead and I'm going to keep the orientation of the voltage source the same, except I'm going to flip the diode this time. And now we have a situation where we're applying the positive to the cathode and the minus to the anode. And so you can see now we're attempting to push current through in this direction, but the diode isn't going to allow that to happen. This is said to be reverse biased. And now hopefully this forward versus reverse biased kind of makes sense with the terminology. Biasing meaning we're applying our polarity reversed, so we're backwards, so to speak. And with forward biased, we are applying the polarity in the forward direction, plus, minus. Current goes through here, and of course it's greater than 0. Sorry, a little bit of a tight squeeze writing that in there. Okay. Now, when we're reverse biased, obviously this is behaving like an open switch to a first approximation, and we get no light coming off of that. Okay, so yes, light when it's forward biased, no light when it's reverse biased. Okay, Now, to get into this deeper understanding, we need to go ahead and talk about a characteristic that every diode has. This characteristic is called the forward voltage. And we go ahead and denote that as V sub F for forward voltage. Okay, every diode has this value. This is a characteristic. Characteristic of the specific diode we are using. So these are devices that you go out and you purchase, right? You don't make diodes. Well, most people don't make diodes. They're quite complex little devices that are manufactured in silicon. We'll actually be, or silicon or germanium. We'll actually be going over the internals and the physics of how they operate in the very beginning of 311. But for right now, we're not going to get into that. We're just going to talk about diodes and how to use them. Okay. As I mentioned, we have this forward voltage, this characteristic of the specific diode we're using. So you go out and you purchase a diode, you use it, and now you're going to be curious what that forward voltage is. Like I said, it's a number specific to the diode you are using. So you would actually find this value inside of the data sheet. So when a manufacturer goes ahead and creates a diode and sells it on the market, they don't just sell you the component, they also need to have some literature that tells you specifics about that component. And so for every single device you ever purchase, there's an associated data sheet. And so you go ahead, open up this data sheet, and you're going to find this value, this characteristic. Now, let's go ahead and make a device, and let's give it a characteristic for this forward voltage, and I can show you how that changes things a little bit. Okay, so let's go ahead, let's give ourselves an LED, and I'm going to have to give you what the forward voltage is. For this example, I'll just say the forward voltage is 2 volts. Now, if we forward bias it, we are attempting to push current in the correct direction. And so you would say that this is forward biased. However, the voltage being supplied, or the voltage being applied to this diode, must exceed the forward voltage in order for current to go through this device. So if I go ahead and make this 1.5 volts, 1.5 volts is clearly less than 2 volts. So in this case, even though we're correctly biased, we're forward biased, we're applying the polarity in the correct direction, but because we haven't exceeded this forward voltage, again, manufacturer value, in this case, we get no light and I is equal to 0 amps. So in other words, this is behaving like an open switch. So it's not enough to just apply the polarity correctly. You must also exceed this forward voltage value if you want current to flow through this device. Okay, so let's go ahead and let's increase that voltage. And now let's go ahead and let's make this 2 volts. Same exact diode. And now it would behave like a closed switch. It is conducting. And so we do get light coming off of this. And we are still forward biased. Okay, so we need to go ahead and meet and or exceed the forward voltage in order to get light off of this, in order for this diode to allow current to flow through it, and for this diode to behave like a closed switch. So not enough to just apply the polarity correctly, also need to meet and or exceed this forward voltage. However, a problem arises here. Okay, so let's go ahead and describe this problem. Once you hit and exceed the forward voltage, the resistance of the diode drops. Towards 0 ohms. Okay? You kind of see what this problem's going to end up looking like. So what I'm saying is, once we go ahead and do this, we're forward biased, and we've exceeded V sub F equal to 2 volts. So this is conducting. This is allowing current to go through. However, this diode is now behaving like a 0 ohm resistor. So this resistor is a stand-in representation for what this diode does once we've exceeded that 2 volt forward voltage by applying 3 volts in this case. Now check out what happens. Notice now we have a voltage applied to essentially a short circuit. So if you wanted to solve for what I is in this case, obviously undefined, but it's not exactly 0. It's just very low. So maybe 0.0001 ohms, something like that. Well, you can see now that this is going to head off towards infinite. Now let me go ahead and ask, you think our diode wants to have infinite current going through it? Of course not. The diode's going to break down. So this diode is going to have its moment of life where it gives off a nice, brilliant, bright red light or blue light or whatever LED you purchased, whatever color it is. But it'll very quickly break down. This thing is going to catch fire. It will let out the magic smoke. Right? So the LED is going to go ahead, briefly work, but that resistance will drop to 0. Current will go through the roof, and this guy is going to catch fire, let out the magic smoke. He's going to break down. All sorts of bad, unwanted things are going to happen. Well, usually unwanted. Sometimes it's fun to blow stuff up. So we need to fix this problem. So how can we do that? What can we add to this circuit in order to prevent this current from going to infinite? Think about that for a second. What can we add to that circuit? Let's see. Well, we've only learned about resistors thus far. So it's a good bet we can fix this by adding one resistor. So let's go ahead and let's do that. Now, if we take our circuit, let's say a 5-volt source, and if we add a resistor in there in series with our LED, we now have some other resistance in series with this diode. Remember, this diode is going to be behaving like a 0 ohm resistor. So we're adding another resistor in series. Series resistance just adds. So if we add this resistor here, we can essentially limit the current from going to infinity. Now, a resistor used like this is called a current limiting resistor. Okay? So the functionality that this resistor is offering in this circuit is that of limiting the current. So we call it a current limiting resistor. This isn't some special resistor that you go out and buy that's called a current limiting resistor. No, this is just a regular resistor that you already have put in series with this diode that is offering this functionality of limiting the current. Okay, so now we can go ahead and do that. But we do still have some questions here. Let's see what some questions are. We're going to still work off of an LED that has a V sub F equal to 2 volts. We'll use that for our example. But how do we pick this resistor value? What's R equal to? How much current is going through this? We need to answer those questions. So let's go ahead and let's phrase the problem such as we want to find a resistor for a given current that's going through here. So we're going to go ahead and say for this circuit we have a desired I, which is equal to, and let's make it 10 milliamps. Okay, so we're going to want a desired 10 milliamps going through here. Now, where did I pick that value? Why not 20 milliamps? Why not 1 milliamp? So, again, if you look in the data sheet, you're going to find something called the max current. This is the maxed current. Also, sometimes it's called the forward current. And that's the max permissible current that you can have going through this diode before it breaks down. Now, I'm working off of the assumption that this is a general purpose indication LED. This is the type of LED that's, in your printer to let you know that your printer is on, or in the bezel of your monitor, your LCD, in order to let you know that your LCD on. So I'm just treating it like a general purpose indication type LED. And if you look up a data sheet for one of those, very common to find that these are about 28 milliamps for this max current or forward current. So then, how do I get to 10 milliamps? Well, just because I can do something doesn't mean I should, right? I can drive this at 20 milliamps, but it's not going to have as long of a life as if I ran it at 10 milliamps. Okay, you kind of have to weigh the pros and cons here. At 20 milliamps, this LED will be brighter. However, at 10 milliamps, it'll be bright enough to serve its function of indicating to the user that something is on or that some selection has been made. So for its intended purpose of indication, 10 milliamps is a good rule of thumb for your general purpose LEDs. So I'm going to go ahead and just say rule of thumb, half of max. This kind of goes for many things in electronics. If you look at the power rating of something, typically you don't want to run things at max. So if you can, try to get close to half of that. In this case, we're looking at current. Max current before the thing starts breaking down is 20 milliamps. However, it performs its function beautifully at 10 milliamps. So I'm going to use that for my desired current. Okay, so now we have a problem that we can solve. So I'm going to start on a fresh sheet of paper here. And let's look at how this problem is set up. We have 5 volts. Going through an LED. The LED is forward biased. We do have positive up there. Let's see. Oh, that's what's happening. My camera's moving a little bit. Okay. So we have 5 volts applied, which is greater than our 2 volts. So we know that this is forward biased and it is going to be conducting. So it should be giving off light. We want to find what resistance value will give us a desired current of 10 milliamps. Now we actually have something that we can solve here. Okay. Now, since the resistance of this diode is behaving like 0 ohms. The only thing limiting this current to 10 milliamps is going to be the resistance over here. However, in order to solve Ohm's law to figure out what the resistance value is for our desired 10 milliamps, we're going to need to know the voltage drop across it. Now, to figure out the voltage drop across our resistor, well, we can use Kirchhoff's voltage law. We start off at 5 volts. We drop some voltage here. Then we drop another voltage across this diode. And then we end up at 0 volts. Okay, so we're going to need to know the voltage drop across the diode in order to know the voltage drop across the resistor. Well, now here's where the forward voltage makes a lot of sense. The forward voltage is the voltage drop across the diode when the diode is forward biased and conducting. I'm going to write that out. V sub D equals V sub F when the diode is forward biased and conducting. I have to say also when it's conducting, because like I said earlier, this supply voltage needs to exceed the forward voltage in order for this diode to be conducting. So this is true when it's forward biased and the diode is conducting. So now we can go ahead and see that across here we have 2 volts. In fact, V sub D is equal to 2 volts. I'm using V sub D. D refers to our diode. Voltage is the voltage drop across the diode. Okay. So now that that's the case, now that we know that our diode has 2 volts across it, figuring out the voltage drop across this resistor is real straightforward, right? Because in accordance with KVL, we can just say V sub R is equal to 5 volts minus 2 volts, which equals 3 volts. Okay, now we can solve this. Now we can figure out what value for this resistor. We can now say, using Ohm's law, V equals IR, 10 milliamps is equal to 3 volts divided by, sorry, I want to write this differently. We want to say that R is equal to 3 volts divided by our desired current, 0.010 amps, which gives us the value of R as 300 ohms. Okay, so that's the answer. Okay, so with a 300 ohm resistor and an LED with a forward voltage drop of 2 volts and a desired current of 10 milliamps, we have an LED that is safely producing light and working. Okay, so once we take the forward voltage into account, this is referred to as the second approximation. Before, when we were treating an LED as simply a switch that's either closed or open, we were performing the first approximation. Now, the first approximation is pretty useful. It lets us easily understand whether the diode should be conducting or not conducting. However, it's not accurate enough to be able to calculate values off of. So that's why we incorporate and start using the forward voltage. Okay, so I'll go ahead and leave that off here. And we're going to pick up next time. We're going to go over AC, and we're going to see what alternating current does with diodes. So we're going to be actually using AC for that, and we'll continue on from there. So please, everyone, take care of yourselves, stay safe, and I'll catch you guys later. All right, take care.